All right, everybody, welcome back to System Software. So today we are moving forward with our compilers. Last couple lectures we were looking at kind of like a high-level intuitive overview of compilers. I know it's a little bit mind-bendy because you have the compiler is the software that is generating software, and if your compiler is written in C, then the C compiler itself is compiling its own source code, or at least the compiled version of that program is compiling its own source code. So I know that's a little bit to wrap your head around, but questions on compiler stuff, questions on how your source code becomes a process, questions on that high-level intuition around compilers, questions on any of this stuff? Everybody's pretty comfortable with it. It's really just your program is spitting out programs. Your program is reading in programs and spitting out programs. That concept hopefully is pretty simple, but as soon as you start reading programs and generating programs, you get to some pretty mind-boggling stuff. All right, let's do homework. Okay, so in class I gave you a grammar for expressions. And I know, not everyone kind of grokked this right at the moment. But here, the idea was to have a grammar. So this grammar is infix because it says an arithmetic expression consists of some sub-expression, which has the same syntax, same shape as expressions, followed by one of the arithmetic operator symbols followed by another expression. That's infix, right? You've got two sub-expressions, and then you place the operator between them in order. What about a grammar for reverse Polish notation? So who's not seen reverse Polish notation? I think everyone should have seen this, right? This is reverse Polish notation. You put the operator after the sub-expressions. And one of the benefits of reverse Polish notation is that you don't need parentheses to disambiguate order of operations. You can explicitly say the order you want because you just read from left to right. So I think most people have done like either an interpreter of reverse Polish notation or a converter from infix to postfix, right? Who's done a converter? I think you did this in like CS. Was it CS1? CS1? Yeah, it's a good exercise. Does anyone recall from the tree perspective, if we have an expression tree, I think this was here. If we have an expression tree like this, how does infix, post, and postfix relate to the tree? Or maybe more generally, what was our algorithm for interpreting a tree? So we had a couple examples here. This was a compiler. This was an infix to postfix transformation. What was like the algorithm? So it was some sort of tree walking algorithm to evaluate this expression tree. What was the algorithm that you learned in CS1? Yeah.
To return the expression as a tree?
Well, to interpret it when we interpreted it.
Using a stack.
Well, a stack is one way to implement the algorithm we're talking about, but a stack is just a data structure, yeah. Yeah, traversal. So we did post-order traversal to evaluate this. And I don't think I covered it exactly last time. But if you do a post-order traversal of this tree, what's going to happen? You're going to get 9, 3 plus, 2 minus. You're going to get postfix notation, post-order traversal. What if I do an in-order traversal? What notation am I going to get? Infix, right? You got to do infix. Does anyone want to see that done? To get into that, raise your hand if you want to see that done, or you're already sort of aware. Want to see it done? Okay. Let's do this. Let's show how the traversals correspond to the syntax of this tree. So if we've got our tree, actually it doesn't really matter what. Oh yeah, that's right. So I'm going to draw my tree a little bit differently to make clear the ordering. So I'm going to call this plus and then minus 2. So if I do a post-order traversal of this tree, what's the order going to be? So I'm going to do both leaves first and then the parent. So here we have 9 and 3, those are the 2 children, and then the parent is plus. For minus this node, the left-hand side is this traversal, and for post-order I do both the children. So I do the child, and then finally the parent. So I cheated a little bit here, because here I was putting the operator here. That's one of the children, so that it wouldn't actually work out correctly. But if the parent has the operator as its data, a post-order traversal will give us postfix syntax or reverse Polish notation. If I do an in-order traversal, what's an in-order traversal going to give me? So I'm going to do 9. I do the left child, then the parent, then the right child, and same for the minus here. So I do the left child, which is here. This is the left child, and then I do the parent and the right child. And I can even show the nesting here. So this is the nesting of them. Questions on that? Does that kind of make sense? In-order traversal? The thing is with in-order traversal, because you have ambiguity, strictly you could put parentheses around each node in order to make it clear what what child belongs to what parent. But anyway, so the main thing I just want to show is that this notion of infix, postfix, prefix, these are connected to an expression tree, which is this syntax of your expression. We talked about like syntax last time. It's connected to the evaluation of the tree, because that traversal order tells you in what order to process these nodes. In order, post order. And and it also shows you how these infix and postfix notations, you can think of them as tree descriptions. So this post order or this reverse Polish notation, it's in some sense a way to represent a tree. So this is one tree, and these are different representations of that tree. That sort of makes sense? Or is that astounding at all to you? But yeah, this is basically a way to write trees in your language. Has anyone ever used Lisp before? The language Lisp or Scheme? Nobody? Its language is basically just syntax trees. You basically write syntax trees for the language. It does not have a language above that. Like in C, you have syntax. But in Lisp, you basically just write the notation. For syntax trees, it has parentheses to show you the nesting of the tree. Sometimes Lisp is called lots of insignificant parentheses as a dig on the language. All right, anyway. Okay, so questions about that? Questions about this sort of brief recap of expression trees and infix and postfix? I remember last time what we did is we showed that if you have the tree, you can generate the postfix version using our special grammar. I don't think I gave a name to it, but you can call it an attributed grammar or semantic actions. But that was just this code here where we had the syntactic description of the node in the tree, and then code that showed you what to generate or what to do when you see that node in the tree. And so we could take this tree and, depending on what code we use to interpret it, we could either directly interpret the value of the math expression, we could convert it to postfix, we could generate assembly code from it, and all those are just different interpretations of this language. And that interpreter definition, that definition of that algorithm for processing the tree, you can call that the semantics, you can call that the meaning of the language. So in this case, the meaning of the language is defined in terms of assembly. Here, the meaning of the language is defined in terms of reverse Polish notation And here it's defined in terms of the actual value you compute when you process that tree. All right, anyway. Okay, so that's a little review of syntax trees from last time. The question was, and parsing is going in the reverse direction. So parsing is taking the sequence of strings without the tree structure and trying to infer that tree structure, trying to figure out what the tree structure was for that utterance, for that sequence of tokens. And for infix notation, we had a grammar that described the order that you would see expressions for infix notation. How can we write this grammar so that it describes postfix notation or reverse Polish notation? Yeah. Yeah, that's exactly right. So the answer is right here. So you would just write expressions consist of two expressions followed by an operator. So a plus expression is one expression followed by another expression followed by a plus symbol. Minus is one expression followed by one expression followed by a minus symbol, etc. And that's one way to write syntax for postfix notation or reverse Polish notation. Questions on that? So that homework's extended, so I guess all of you hopefully will get it right. All right, any other questions from the compiler overview stuff, from the homework? Okay, okay, so, what's the question?
I was curious, what actor do you think would play you in a movie? Like if you're writing a movie.
All right, so today today is kind of about introducing the compiler project, but I'm also going to go over a bunch of kind of like stuff you'll need for this, like the x86 assembly language, how memory layout works, just an overview of it, and then basically the rest of the course is going to be going over how we actually compile our language. And I'm going to also show you the language that we're going to compile. So we're going to write a compiler for this simple language that I've designed for you. So just as a little refresher, remember how source code becomes a process. You start with your source code. The output of the compiler and linker and all the language tooling is an executable, and then the loader in the operating system takes that compiled machine code, puts it into memory, and starts executing it. So we're going to be doing this part here. We're going to be doing the part that takes source code and turns it into assembly language. So we're going to reuse the rest of this tool chain. So we're going to reuse the existing assembler, the existing linker, the existing loader to do this. We're not going to do any pre-processing stuff, although you could if you wanted to. But yeah, we're going to just write this component ourselves. It's not going to be for C. We're going to do it for a simpler language. And then the way we generate our assembly code is going to fit with the linker and the loader so that we can reuse the rest of this tool chain. And we're not just going to, it's going to be a toy compiler, but it's actually going to integrate with the Unix development environment. You'll be able to take your assembly output and actually make an executable program. You'll even be able to link with C programs. You can write C programs and link with your own program, and you can actually call C code. You could call it malloc if you really wanted to. But yeah, so that's the task, is to write a small, simple version of this compiler. I shouldn't say simple, a small, short version of this. It will be a little tricky, but it's a small version of this compiler. So just to make it clear what it is we're doing, we're going to be writing in this language that I call simple IR. This is going to be our input language. So remember what a compiler does. It takes an input language. In this case, it's going to be source code. The language is going to be a teaching language I invented called simple IR. Your program is going to be called CodeGen. And the output, what's the output of our compiler going to be? What's the output? Assembly. It's going to be assembly code. It's going to be assembly code. And the architecture is going to be x86-64, specifically for the Unix-like systems. We'll get into the so-called ABI, the Application Binary Interface, when we get to functions, but it'll be a specific format and a specific binary interface that will work with all of the other C code, all of the other compiled code on your machine. So questions about this, the overview of what we're doing. So remember, we're writing CodeGen, and we're going to write it in C++, but don't worry, I'm going to give you all the C++ stuff you need. C++ is C plus extra features. The input language is not going to be executable or interpretable anywhere. There's no machine that runs it. The CodeGen is going to do what we did for expressions last time. It's going to interpret this input language and generate, well, I should say it's going to compile, but it's going to ascribe meaning to the input and generate assembly code as the output. Exactly what your C compiler does. Questions on the overall goal of this project for the second half of the class? Everybody clear? Everybody good on what we're doing? So remember, the hard part about this is we have 3 languages here. We have simple IR, this language I'm going to show you today. We have C++, the language that the compiler is actually written in. And then we have x86-64 assembly language. So this is the really, really tricky part about writing compilers. That there's 3 languages we have to keep track of at the same time. And we have to remember that this input language is not something we're running or we're solving, we're translating it. So we need to understand the input language and understand what equivalent output looks like for that language. And then we need to understand the language we're writing our compiler in and write code that will generate equivalent output code for our input code. Questions on this? I mean, I know you probably have lots of questions about how to do it, but questions on the problem statement. Everybody good? Okay. Okay, so it's no easy feat, but okay, so let me give you so this is an example. So this is an assignment statement in this simple IR language that I'm gonna give to you. And it's very close to C. So it's almost like a simplified version of C. Anyone guess what in simple IR this statement is supposed to do?
X plus,
What's that?
no, I was going to say X plus equals, but I saw that the X plus 2. So.
Yeah, I'm using the colon sign here, but you probably don't see that in C, right? Pascal maybe has that. Anyone want to guess what this means? You don't have to. You shouldn't know because remember, language symbols don't have any meaning unless you have some semantics, some definition of the meaning. But I'm just wondering if you can guess how I designed it.
Adding 2 to x.
Yeah, it's just adding 2 to x. It's just x equals x plus 2 in C. That's it. And this is what the assembly code might look like, equivalent assembly code for C as well. Now, this is probably a little bit more mind-boggling to look at, but let me just walk you through it in a hopefully simple way. So we'll go over all this syntactic stuff. The x86 assembly in the Unix world is a little kind of makes your eyes glaze over a little bit. But since I think you all did computer org and you used MIPS, what this is doing is actually pretty straightforward. It's loading this memory location. So this is a memory location. It may not seem like it, but this is a memory location that's derived from an address and a register. So it's like a pointer or an array index. Taking that memory location, storing it into a register. It's taking the constant value 2, storing it into a different register. So we have the A register and the B register. And then it's performing an addition on those 2 registers. And finally, it's storing the result back into memory. So read the value of x from memory. Oh, not load A and B. Read the value of x from memory. Store 2 into a register. Add those 2 registers together. And then store the result in x. Questions about what the assembly code is doing? I know you probably have lots of questions about the syntax and the full syntax of x86, but any questions about what the assembly code is doing or why it's equivalent or not equivalent to this code? Everybody's like totally good with this? Believe the x86? Okay, so there's a bunch of issues here. So how do we get this? How do we know that this gobbledygook means load from X? And we'll get into that in a few weeks. But the simple 4 steps here is load the values for the operands into registers, do the actual arithmetic, and then store the value back into X. So there's our assignment to X. These are our operands here, and then the plus symbol gets defined as the x86 add operation. Questions on this? Everybody pretty good on this? So the job of our compiler will be to take text like this, just straight up ASCII text, and generate assembly code. This will be the output of your compiler. This will be the input of your compiler. Okay, so let's take a look at our input language. Let me walk through what our input language looks like. So here's a C program. Take a second to digest it. Got 2 variables being declared here. X is being assigned to the output of this readInt function. I haven't defined it, but it's calling a function here. Ret value is being assigned to this function call here, and then we're returning 0. Questions on this C program, the meaning of this C program? Hopefully everybody should be good on this one. But any questions if you have it? Okay, so this is what the equivalent simple IR looks like. Like C, we have to declare all our variables, but there's no types here. Everything is just a 64-bit number in my language. This is how you declare parameters. And function calls look like this. You just say call and the name of the function, and it always has to be assigned to something. This is how you do, I didn't have multiplication in here. Okay, this is not exactly equivalent. Oh man, I messed this one up. But this is how you would have multiplication. It looks like our arithmetic from before, and a function call, return, and end function. So it looks really similar when we have a simple C program, I'll get into the differences with simple IR. But there's an example. So what's a little different from C is that each compilation unit, that is each simple IR file, is a single function. So C allows you to define multiple functions. That just makes compilation easier. This is what a minimum simple IR program looks like. It's just defining one function, and you have to have a return value. In C, you don't have to have return values. You can have void functions. But here, every function returns an int. When there's parameters, you specify them with this parameter statement. When there's local variables, you specify them with this local variable statement. And then all of your actual operations go in between the parameters and the return. Okay, so let me go over the kinds of statements you have in simple IR. You have assignment. So there's only 2 kinds of assignment in this language. There's either assigning to a constant value or assigning to another variable. That's it for assignment. Just actually kind of similar to C. You also have arithmetic, and arithmetic only consists of a single operation. So unlike C, you can't string together arbitrarily long amounts of expressions. There's a single operation at a time. Why might it be easier to compile this to assembly than, say, arbitrarily long math expressions? Well, you wouldn't have to care about order, yeah, for sure. You wouldn't have to care about order of operations. So there's no need to define order of operations here because you only have a single operation at a time. What else? So does the architecture support math expressions? Is there any operation in MIPS or x86 that will compute a math expression for you? No, right? What do you have at the assembly level? Add, like do one add. If you have a math expression, you have many, many arithmetic operations. So this simple IR is designed to be closer to assembly. So IR stands for intermediate representation. I talked about this a little last time or maybe last week, where we have a lower level version of a language, so it's something in between C and assembly. And this simple IR is a version of that, where it's less assembly-like. It doesn't have the details of assembly, like you don't have to deal with registers. You have variables here. You have function calls. But it's simpler than C in that often each statement in the language corresponds to one or a small number of assembly language operations. So this design will just make it easier to do compilation. So anyway, so that's arithmetic. I'll go over arithmetic next time. This is what function calls look like. Syntax is a little different. You don't have parentheses. You say the call keyword here. That just makes it easier to tell whether it's a function call or not. You can't use call as a variable name. And then you just list the arguments. One other subtlety here is that the arguments have to be single variables. You can't put math expressions as arguments for functions. Again, same reason, because this corresponds much closer to one or a few assembly operations rather than a C function call, where you can put arbitrary expressions that all have to be computed before you can even do the function call. All right, so that's what function calls look like. Branching is also simplified. There's no if statements or while loops. You only have go-tos in this language. So here we have a conditional go-to. Again, this is also really close to assembly language. Just like, has anyone ever used go-tos in C? Or are you always taught like never use go-tos, maybe? So at the assembly level, there's no such thing as an if statement or a while loop. Instead, there's just unconditional branches and conditional branches. Anyone not familiar with conditional branching, unconditional branching? I think you all should learn this in computer organization, right? Everyone should learn this. So this is how we state a conditional branch in our language. The if go-to is a keyword. We put, without any math expressions, just a variable or a number. They can be compared, and if that comparison is true at runtime, then we branch to the label. So what might the C if statement equivalent of this program look like? So let's try decompiling this, this program. Any takers on what a C program equivalent of this might look like? So let's say we already have our variables declared. What's an equivalent C program to this simple IR program? Yeah. Uh-huh. Okay, that's a good, nice syntactically similar program. Then else what? Okay, so nothing here. Anyone have a different answer? Anyone agree, disagree? Go on. Ah, okay. So
Because it's saying if go to x is greater than 0, go to end later. So if x is greater than 0, then you want to go to the end of the program. Essentially.
so we have like this, right?
Yeah.
So what the colleague observed. So yeah, this looks very close to like an if statement where we've got a body of an if statement here. But notice, as your colleague astutely pointed out, that this is skipping what looks like the body, skipping the statement if this is true. And you'll see this a lot if you ever want to work with like malware detection or binary disassembly or looking at assembly. The compiler will actually invert the logic of this because you're skipping the body. You want to know the condition when you skip the body, not when you go into it. So subtle difference just to pay attention to. And you also have to worry about that when we actually do the compilation. But yeah, this is exactly right. So notice that this says if x is greater than 0, we skip this line. So this is equivalent to this simple IR. This is not equivalent. It's actually doing almost the exact opposite thing. Another way to write this is if x is less than or equal to 0, then run this code. Make sense? We just inverted this logic here. So if we invert this, negate this, then yeah, we get the same behavior as this program. Questions on this? So good catch, something to be aware of when you're dealing with assembly versus C. Yeah, then there's also an unconditional branch for goto, for unconditional branches. All right, pointers. We have pointers in our language. So we're going to actually learn at a very low level how pointers are implemented. And who likes pointers? Who thinks pointers are fun? Okay, some people. They're pretty fun, right? So if they're really fun for you, then you'll see how they actually work under the hood. To me, it makes it actually easier to understand them. And if you've been confused by pointers, then I think this will actually help you understand what's going on under the hood. Because it's actually not that bad, what they're doing. So we're actually going to implement the three main things that we have in C: getting an address, add the address of operator, dereferencing a pointer, and doing a dereference assignment of a pointer. So notice, we can't dereference a pointer in an expression. We can't get an address in an expression. This is the limits of what we can do in our language. We can assign just the address of a variable. We can't add to it. We can't do any other complicated dereferences with it. We can only dereference a variable. We can't do that in an expression or an arithmetic operation. And we can assign to a dereferenced pointer. We're going to do that in a couple weeks. It's a little confusing, but the code ends up being really, really small and simple. It's just the idea behind it is really pretty complicated. All right, so, so here's a example program computing exponents. So this is just our definition of the function. This is our kind of epilogue of the function. So this function has three variables, base, x, and result. Two of those are used as parameters to the function. We're going to return the result variable. And it looks very much like the assembly. If you remember the assembly we did for exponent when we wrote our little toy compiler. So this will just set result to 1. We've got a label here. Here's its corresponding unconditional jump. So this is like a while loop. So if exponent is less than or equal to 0, that is, if we've already finished computing the exponent, then we branch here to end the loop. So just like we had in C, this is like saying while exponent is greater than 0. You see that? So just like with the if statement, we're leaving the if statement, or leaving the while loop. If exponent is less than or equal to 0, that means we stay in the while loop when the negation of that is true, when exponent is greater than 0. And inside the body, we do result equals result times base. And then exponent equals exponent minus 1. And then return result. Questions on this simple IR code or its C equivalent? Hopefully it's a straightforward C code too, but let me know if anything is puzzling. Okay, so this is an example complete program, or complete function I should say. All right, the grammar is given in the assignment, but I guess I should go over it quickly. This is very ugly. Let me get the actual grammar. So there's some reading for tonight on the parser generator that we're using for this class, so you're not going to have to write your own parser. I've given you a grammar already for this language and a parser generator called Antler, which will take that grammar and it'll generate code that when run will give you a syntax tree for this language. So you won't have to do any kind of parsing like you did for Bash. And this is just a definition of all the statements in the language. So a function looks like the word function. So if we look at our complete example, we can see that this grammar defines the general schema for the syntax, what all programs look like. Yeah?
So loops in simple IR use the go-to grammar?
Yeah, use the go-to statement, yeah.
So
Yeah.
if we have a go-to, then will it also use the go-to grammar? Like, do they share that?
You mean a go-to in C?
Yeah.
Yeah, it'll behave very similarly. Yeah.
So it'll use the same grammar in simple IR?
Well, the grammar will look really similar in C. So it'll be like go-to followed by a label. But remember, we're not compiling from C or to C. We're compiling from here to assembly. So we're going to be translating this goto into the x86 version of unconditional branch, which is jump, JMP. But yeah, I mean, this whole language looks really close to C. So, but it's not the same language, even though the grammar might be similar, because yeah, C has all these other features that aren't available in simple IR. But yeah, it works just like goto in C. Okay, so anyway, you can kind of go through this yourself to get a sense of this. I know I only went over grammars really briefly, but you can kind of see each of the statements defined here. So this is the parameters string followed by one or more name tokens. A return statement is the return name followed by either a name or a number, or sorry, return keyword followed by a name or a number, and so on. So you won't have to worry too much about how this grammar is made. I'm going to walk you through using it as we talk about compiling each one of these constructs. But I just want to kind of show you that, the what we did as a toy last time for expressions defining syntax, we can do this for real programming languages. This is how programming languages get defined, by defining their syntax. Okay, so that's the grammar. All right, the way we're going to implement this is just like what we saw for the scheme we saw last time, where once we have the grammar for it, the job of our compiler is going to be to recognize that we've seen one of the statements in our language, one of the syntactic constructs in our language, and then we're going to write code which is going to generate our output language. So in this case, this is going to be the simple IR constructs like arithmetic or function calls or assignment. And then in our C++ compiler, we're going to write C++ code here that will spit out assembly. So this is going to be like simple IR. This definition of what the compiler does is going to be in C++, and it's literally going to print out assembly code. Questions on that? So let me show you an example of this before I go on. So there's a extensive documentation for our compiler, our handbook, and I'm going to show you what some of the given functions look like. So the cout is just the C++ way of doing printf. And here, notice, we're literally printing out text. We're printing out a move instruction with some operand given to us and a register name. And we're doing another move from that register name to another operand. So don't worry about the details of this, but I just want to show you that this is the code that your compiler will use, or will write. You'll write this for your compiler. And all it's doing is spitting out assembly code. It's literally printf assembly code when it sees a certain construct in the language. And the way Antler works is for each one of these constructs in the language, like if we have an assignment statement or we have an arithmetic statement, Antler will give you a function that you can implement. And when the parser sees an assignment statement in the input language, this code will get executed. That sort of makes sense? So it's this same scheme here, but we have a real parser framework. We have a real tool, compiler tool that we can use to actually implement this on a real machine using real code. Okay, questions on that? Oh, sorry, yeah. I'm sorry, second? The last slide?
Yeah, that's showing the grammar.
This one? Yeah.
So is there something being ran that will check the simple IR and then run the C++?
Yes, exactly.
Okay, it's not running the C++ is to check the simple IR?
No, there is, so that's the parser. That's what the parser does. So the parser will generate the syntax tree, and then there's just a tree walking algorithm in the parser framework that will just walk that syntax tree and then trigger each of these snippets of code. So these are called semantic actions. That's the fancy word for them, sometimes called an attributed grammar. But it's just a general way of defining these, where is this? This was here from last time. So if you remember last time, we had multiple different ways to process this tree. We could either interpret it by getting the resulting value, we could generate postfix notation, or we could generate assembly code. This concept of walking the tree and triggering code to run whenever you see a certain syntactic unit, this is called the visitor pattern, or tree walking, a tree walking algorithm. So the parser framework I gave you will do this for you. It will do all the work of reading in the input language, generating this tree, and then walking the tree for you. And all you have to do is write a snippet of code to say what happens, what should this parser do whenever it sees each construct. Does it kind of make sense? So this code will run whenever an assignment statement is input by the user. So if the parser framework sees an assignment statement, this is the seed code that'll get run. And so the way you implement a compiler using that framework is whenever you see an assignment statement, you spit out assembly code that is equivalent to an assignment statement. Kind of make sense? And I'm going to walk you through, like for each construct, what you spit out and how you use the parser framework to do it. But I just want to really instill that concept in your head of what this parser framework is doing. Also, I gave you reading, which maybe nobody did, but I gave you reading for the Antler. The Antler is the parser framework that we're using, and this will walk you through some examples of this tree walking concept, language definition and tree walking concept. So basically, if you've got a grammar for your language, then you can define a compiler by just saying what happens when each statement in that language gets seen by the parser. And when you want to make a compiler, you just spit out your output language. Because remember, what is our compiler doing? It's taking the input language and spitting out assembly. It's taking simple IR and spitting out assembly. So half the compiler is written for you. The parser will read in that input language, make a syntax tree, and then it'll call these functions for each of the syntactic units. For assignment, for arithmetic, for branching, it'll call a C++ function, and you just have to write what that function should do. How should that function output assembly code? Questions on that concept? Questions on that? Am I beating a dead horse yet? All right. Okay, so these, just from some terminology, you can think of this is a semantic action. This is basically a semantic action. It's called something a little bit different in Antler, but I'm going to call this a semantic action. It's defining the semantics, defining the meaning of the language. It's what do you do when you see that part of the language. So those are semantic actions, and that's your job as the compiler writer, is to write these semantic actions. So we're going to use Antler for this. Please read the Antler book. So these are free online. These readings are here in the syllabus. Read these. This should make it clear. Terrence Parr is a really good writer. He's the creator of this parser framework, and it's a fairly usable parser framework. You can actually use this if you go out to work and you ever have any language processing stuff that requires configuration language or domain-specific languages. You may encounter using Antler. It's a very popular tool chain. All right, questions on overall kind of idea of parsing, parser framework, what we're doing for our compiler. Questions on any of that? Okay. All right, so let's go over x86 Intel a little bit. This stuff this is very low level, but I'm only going to show you the things you need for writing the compiler. So you don't have to be an expert in x86, but you do have to understand a little bit of like the computer organization stuff. So hopefully this stuff is a little bit review. Has anyone seen a diagram like this in like computer organization? Where you talked about the layout of memory. Okay. So So this is the x86 world's memory layout, and it's shared by lots and lots of other architectures. So this is what your running program has in memory. It has the text segment, which is where your actual machine code lives. It has a data segment that's effectively for global variables. And then you have your stack. So from computer org, what is the stack for? Why do you have a stack in memory in your running program? Was that? Undo. Okay, stack could be used for undo, but that's not the use of it here in your running process. But absolutely, you can use a stack for undo. You can use stacks for lots of things. Why does your running process, why does the operating system bother to give your process a stack? Was this in computer org? No, I don't. No. So the stack is for function calls. Have you ever encountered a Stack Overflow before? What happened with a Stack Overflow? How did you get to a Stack Overflow? You had one, right? What did you do or not do?
Added too much stuff to the stack. I did a recursion call.
Recursion. You did a recursion, right? So you added too much stuff. You had an unbounded recursion. And what happened? You just did an unbounded number of function calls. You kept calling the function. You kept calling the function over and over and over. The stack stores the state of your function call. That's what the stack is for. That's what, the website Stack Overflow. Stack Overflow is such a kind of common mistake, especially when writing recursive functions. That's why you get it. We're going to learn how the actual stack is managed. But this notion of using stacks for function calls is so integral to systems, and so integral to software, that the operating system actually provides you support for this. And the architecture does as well. There are actual machine instructions for managing a stack in memory. So these are the parts you have in memory for your program. You also have the heap, which I didn't actually. I guess this is the heap. This is the heap. This is probably globals, and this is the heap. The picture above here, this is your executable file. So this is what your program looks like on disk. It has other information, header information, but inside of it is your machine code segment and your global variables. Why is the stack and the data segment not in the executable, or why is the stack not in the executable file? Very subtle question. Well, the stack is for a running program. So just like when you call malloc, though that malloc data is not in your executable program, it's not in the program. It's the state of the running program. But anyway, we'll get to that a little bit more when we actually talk about functions. Functions is the hardest part of this. All right, any questions about this? So this is just what your RAM looks like when you have a running program. You have your machine code, you have your heap, and you have your stack. And hopefully you learned about its computer organization, but maybe not in much detail. So anyway, so in the assembly file, you can actually specify these segments, so you can say where the machine code segment is, you can say where your global data segment is. These are the register names in x86. They're in the syntax we're using, the GCC syntax, which is the AT&T syntax. They're prefixed by a percent sign when they're being used. But these are the names of the registers that we're going to be using in this class. That's it. We're only going to be using these 5 registers. I'm pretty sure that's all it is. I checked through my compiler. That's all you need for it. So there's basically going to be 3 general purpose registers. For short, you can call these A, B, and D. A is historically the accumulator register in the Intel world. B is for base, for memory stuff. D is for data. D is going to be used for division as well. You could think of D as division. But for most of our operations, we're really just going to be using the A register and the B register as storage. Questions on that? Questions on these registers? I think you all know about registers, right? Using registers. And then there are 2 other special purpose registers. One is the stack pointer. So the architecture actually provides a special register that is meant to point to the top of the stack, and there are operations for pushing and popping from the stack. And there's something called the base pointer. And this one is going to be a lot more confusing to explain because it's not something you see in C language, not something you see in high-level language. But this is how you're going to access local variables. Local variables are going to be pointed to by this register in the Intel x86 world. So this is for local variables. This is for the stack, which the function calls use. And these are the general purpose registers we're going to be using for arithmetic and other operations. Questions on that? So these are the only registers you'll need to know from the x86 world for this class. All right, so let's look at all of the operations we're going to use in this class. So there are a number of them, but it's definitely not we don't have to learn the whole x86 architecture, which has hundreds of operations. So one of the main ones we're going to use is move. Unlike the MIPS world, in x86, move is the mnemonic for both reading and writing to and from registers, and also to and from memory to registers. So they're all move, even indirect, like pointer-like movements. All is done with this move mnemonic and just different arguments. For arithmetic, we're going to be using these 5. So add, subtract. These are all integer operations. Add, subtract, multiply, divide. This is used for division because in the Intel world, you have 128-bit, what's it called? The quotient? I can't remember the word for it. But the top of the division, the left operator of the division is actually 128-bit, and then the bottom of the division is 64-bit. But we'll get to that. But yeah, just 4. We're only going to do 4 operations, arithmetic operations in this class. These are our branch operations. So you have unconditional branch. It's called jump, JMP in the Intel world. And then you have conditional branches. So the way you do a conditional branch in the Intel world is you first run compare. You compare 2 values, and then there's a different instruction for each of the different results of the comparison. So if you want to jump when the comparison was not equal, you use J and E. If you want to jump when the comparison was greater than or equal, use this. So this is how we're going to implement, greater than, less than, equals, not equals. Questions on these? So these are just different variations of the same conditional jump. This is all just conditional jump. And you run compare to test the condition. And then for functions, there are some special purpose operations that'll help you with functions. So push and pop, we're going to use those for functions. So the call stack, the stack is going to be used for tracking nested function calls. And then we have special call and return opcodes, which are called call and return, but they don't actually work the way you expect for like C-like functions. So all call does is save the return address and then do a jump. And all return does is pop that return address and jump to it. So nothing with parameter passing, no recursion, no nested stuff. But anyway, that's all of the opcodes you'll need for the Intel world. So just moving data around memory and registers, arithmetic, branching, and support for function calls. Questions so far? So, and I'll go over in detail each of these operations when we actually go to translate them. But that's the code you're going to be outputting, this Intel code. All right, so one subtle part about the assembly language that we're going to be generating what's called AT&T syntax, which is like the very old, decades-old assembly syntax from the AT&T Unix world. But this is the default used by GCC. So we're going to be using the GCC toolchain to finish linking and producing an executable out of our programs. And so the one thing to keep in mind, the one kind of gotcha in this, is that the destination operand is always on the right. So if we have a move operation here, the left operand, that's the source. The right operand is the destination. So to write this in C-like syntax, so I have move RBX, comma RAX. In a C-like syntax, that would be written as RAX equals RBX. Questions on that? Is that kind of clear? So you just kind of have to remember that the second is not clear. The second operand is the destination. So that's the left-hand side of the equality sign in C. Questions on that? That kind of makes sense. So you just have to remember that this is the syntax. Now this becomes really confusing when we have arithmetic operations, because the right operand is not only the destination, but it's also the left operand of the addition. So if I have add RBX, comma RAX, this means RAX equals RAX plus RBX. So the operands are switched. This doesn't matter for addition because it's, commutative? But subtraction, division, they are not commutative. So this ordering matters when you're doing that. So if you encounter a weird integer arithmetic bug where something's negative when it shouldn't be, or vice versa, it could be this parameter switching problem. So remember, destination operand is second, is last, even for arithmetic operations. Okay. All right, so here's an example, simple IR example. We're declaring 2 local variables, and we're assigning x and y to 2 different values. So in memory, the way this is going to look is we've got effectively an array in memory. So the way the compiler and machine, oh, this again. This is such a strange bug. Okay, so the way the compiler and the operating system work together to store your local variables is they basically just, in memory, in this stack section, they'll create effectively an array to store all of your variables. Now remember, what does RAM use symbols like X or Y or Z or strings? Can you access RAM by giving it a string? How do you access RAM locations? Addresses, right? So one job of the compiler is to take these symbolic names, these string names for variables, and translate them into addresses. And that's a very tricky problem because where do you put them into memory? Do you always put them in the same spot? What about function local variables when you call the function multiple times? So what part of what the compiler's job to do is to figure out where in memory to put these variables. And the way this is going to work is let me make a nice array here. Is the way this is going to work at the architecture level is we're going to use this RBP register as a pointer to our array of local variables. So let's say we put X and Y here in our array. Now in our language, everything is going to be 64-bit, so this slot is offset -0, this slot is offset -8, this slot is offset -16, this slot is offset -24. Now in conventional diagramming, the high address goes up here, the low address is here, this is the low address, this is the high address. And for reasons that we'll see when we actually get into how this is implemented, we store this as offsets, negative offsets from our array. So you can really just think of this as X being the same as RBP minus 16. So we're going to write our compiler so that it'll make this translation of X, but in this memory layout that I have here, you can think of RBP as being a C-like array, and then you just index into it by offsets. So we'll see how RBP actually gets its address, but if you think of RBP as a register that just stores a memory address, then we can allocate space like an array for each of these local variables. So that way, if we see X in our input, we'll have a way to translate it into some assembly operand that the machine can actually use. So X and Y is not something that the machine uses for addressing, so we have to translate this into some memory access for our move operation to work for assignment and operands. Kind of makes sense? Does that make sense? So we just need to be able to lay out memory to store our local variables, and whenever we see those local variables, we need to translate it into some assembly operand that will access that memory location. Now, how you actually do that is a little tricky. We're going to do that when we talk about functions, so I'm just going to give you what's called a symbol table, and I have the code written for this for you. But in your compiler, the symbol table is going to track and map names and offsets. So when that local variables, when this local variables statement is evaluated, I've given you code to do this already, it will generate this table, this in-memory table, that will keep track of a mapping from symbol names to offsets from RBP. So this is what, this is the same. This is what the symbol table will look like for this program. It'll just put them in order, starting from -16 and adding 8 for each offset. So questions on this idea where stuff is stored in memory and we have a symbol table? Yeah.
Why is X a -16?
So we'll see the reasons for that, but basically it's because the heap grows upwards in memory when you do malloc, and the stack grows downwards in memory. It's a kind of an architectural trick, so you can have two data structures in memory and not have to like predefine their size, even though, I mean, there are maximum limits, but just by convention in like modern systems architecture, the heap grows upwards in memory and the stack grows downwards from the top of the address space. So that's why the array in memory goes down, or the array in the stack goes down. But just remember it as a convention. We'll see it actually in practice when we go to implement this, and we'll see some of the security implications of this decision. But this is how most systems, I think Windows, Linux, Mac, these will all work the same way, where the stack grows downwards from the top of memory. But yeah, just think of it as this is what's sort of given to you by convention, and then we'll see where it comes from in a couple of weeks. But this is given to you by convention. RBP is like the array that stores your local variables, and your compiler defines which memory location or which slot in that array that variable will be stored. Yeah.
So what you were asking, are those arbitrary values or?
No, they're just going to be, they're going to start from -16 in our compiler, and they're just going to go down by -8. So 8 bits for each. So in our compiler, each variable is 64 bits. That's 8 bytes. So if we have another variable here, like p, that's going to be -32. Okay. So for our compiler, now in a real world compiler, you have variables of different precision, different sizes. So the compiler will actually have to keep track of how much space to allocate. For us, it's very simple. It's like a simpler. It's a 64-bit array basically that grows downward in bytes. But yeah, this is just for doing like allocation, memory allocation for our local variables. So this is going to be given to you, so you won't have to like compute all this, because it's annoying to compute. But what you're going to get, which I've given you code for, is something that's going to generate this symbol table for you. So you won't actually have to work with these numbers. You'll just do lookups to the symbol table to see, okay, where in memory is this variable stored? And then when you have like a variable access or an assignment, you'll just look up in the symbol table where in memory that variable is stored. So okay, so just very quickly, so what the consequence of this is, if I have assignment from x to 3, this is what the Intel x86 assembly looks like. We store the constant value 3 into the register A, because remember the destination is on the right, and then we store the register A we store it into memory. So this is the assembly language syntax for basically array index. So this is saying, give me the offset from this address, give me -16 offset from the RBP address, and compute that address and store whatever RAX is into there. So this is the equivalent of x equals 3. Yeah?
You can't combine that stuff?
Good. This you could combine. I don't, because it's easier to write the compiler, but you can't do 2 memory accesses at the same time in a move. So if this were like x equals y, you would not be able to do that in one instruction. All right, so I am a minute over. Yeah, that's actually all I had to cover. So see you all next time. Let me know if you have any questions. Next time we'll actually get into arithmetic.